Hi everyone, welcome to last part of lecture 5, and in this lecture, in this part, we will cover the Poisson distribution. But before giving the um, the theoretical formulation of the Poisson distribution, let me give you a problem to make things more clear, okay? And I hope by doing this, you will have better understanding about the logic of the Poisson distribution. So let's say that you are hired to analyze the performance of supermarkets checkout lanes, okay? And you need the distribution of the number of customers entering to the particular lane in a particular hour. So let's say you are an analyst and you will check the customer and maybe you will record when the customer arrived to the store, okay? And you know that on the average, the Lambda customers arrive in an hour. So in that point, assume that the arrivals are equally likely at all times within that hour. And the number of arrivals during an interval is independent from the history of arrivals outside this interval. So what I mean, let's say from this point to this point, which is a 1 hour, the first thing is to assume that the arrivals are equally likely. So the probability of any customer arrive to the store at this time, let's say it's T, will be equal to the probability of any customer arrives to the store at that point. Okay, they will be same. And also, these two arriving process will be independent from each other. They will not be affected from the past. Okay. And the question is how can we approximate the distribution, the probability log of the arrivals? So let's divide this 1 hour, this part, this part, which is time 0 to 1, and we have 1 hour here, into a lot of time buckets. Like let's say these are the buckets, okay? So in each buckets, the arrival of a customer is independent Bernoulli trial, right? So because they are independent and they will be equally likely, and we know the total time buckets. So the trials, the number of trials, let's say. So if the Bernoulli trial results in a success for a particular time bucket, that means a customer arrives in that interval. So if the result of this bucket is success, that means a customer arrives to the store. This is we call the success. If there is no arrival in that time, so that will be labeled as, or that will be the event of failure. So what is the probability mass function of total number of arrivals? That means we can, maybe one customer will arrive, maybe 0, maybe 2, maybe 3. So just we need to calculate all possible values. So all possible arriving number of customers, and this will give us the probability mass function of such a model. So how can we approximate the distribution of the arrivals? Okay, let's first understand the basic logic of the Poisson distribution and how we can use a good approximation. So the total number of arrivals has a binomial distribution, right? We say that because let me open a new page, and let's say from this time interval, we have split that time interval into some number of time pockets. In this case, the time pockets is 5, right? So we have split that time interval into 5 time pockets. And what was the average customer arriving to the store during that time interval? That was lambda. And we expect that these time buckets are equally likely and independent from each other. We have say that the lambda or 5 customer will arrive to the store in that specific time buckets, right? And if these are the Bernoulli trials, we can think that that number of arrivals has a binomial distribution. Okay, let's start by writing the PMF of binomial distribution, which is n choose k, p to the k times 1 minus p to the k. Okay, so what this tells us? Let me change the color. Let's say during that time interval, the one customer arrived to the store, and let's say the customer arrived to the store at this time pockets. How can I calculate this probability, the probability of one customer will arrive to the store by using the binomial distribution? Simply that, which is 5 choose 1 divided by p2 1 times 1 minus p to the 5 minus 1, right? Why? The first thing, let's look at this part, which is actually the probability of success in our context, which is the probability of arriving customer. We have only one, so the probability of this one is p, and other time buckets there is no customer, so that's why the probability is 1 minus p. And we have 4 time pockets. In that, the customer didn't arrive at the store. Okay, so that's why I will calculate the product of them. But one customer can arrive to the store in 5 different time pockets. He or she can arrive at this time pocket, this time bucket, this time, and this time bucket. So I have 5 different options. That's why I choose it. So let's say what was the mean of the binomial distribution? That was the NP, right? We have calculated in the binomial distribution lecture. Okay, that was the mean of the binomial distribution. And what is the mean of the Poisson distribution that is given to us, which is lambda, right? Which is lambda. So I can say that the lambda is equal to n times p. And instead of p, that means I can write n divided lambda divided by n, and that will be 5 choose n, lambda divided by n 1, and let's say 1 minus p, so 1 minus lambda divided by n times 5 minus 1. So this is the specific version for n is equal to 5 and k is equal to 1. But let's do it in a generic way. In this case, it will be n choose k and lambda over n to the p and 1 minus lambda over n minus k, right? So this is k, sorry. Yeah, this is k. Okay, so in this one, I have split that time interval into 5 parts. But what happened if I splitted it into 10 parts? Let me draw it. Let's say, which is the time interval, and we have split it into 5 time buckets, and I have some customer arrive to the store at, let's say, this point, and this point, and this point, and let's say this point. But let me do it better here. Okay, so what happened if I split same time interval into 10 time buckets? Okay, I have same time interval, and I'm gonna split it to 10. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So now what happened? This customer arrived at this point. This is in this point. This is in this point. This point. This point, and this one, this point. So what was our expectation is the number of customers in each packet will be the same, right? That was the lambda over 5 in this example. But now in this one, one packets have more customer than the other, right? In this time buckets, there is only one customer. In this time buckets, there are two. But if I divide into some more number of packets, the packets will now have same customers, same number of customers, right? 1, 1, 1, 1. So that means that the smaller buckets will give us a much more approximation, much more better approximation quality. Okay, so that's why if I want to get a really good approximation, what can I do? Simply, I can divide this time interval into infinite time packets. That's mean n will go to infinity. Okay. So if that is clear, what can I do with the PMF of the binomial distribution? So what I am trying to do, just by using a binomial distribution PMF, I want to get the Poisson distribution PMF by increasing n infinite. Okay, and also, so that's mean I can say that the differences between the binomial distribution and the Poisson distribution is that in binomial distribution we know the number of trials n is a constant or n finite. In Poisson distribution, on the contrary, the n is infinite. Okay, so the only thing what I need to do is just calculate the limit of the binomial distribution when n goes to the infinite. Okay, and at the end, I will be ended up with the PMF of the Poisson distribution. So let's do that. So what was our the PMF, the probability mass function? This one, right? This one. And let's say the n goes to the infinity. First, let's open this part, which is n factorial divided by n minus k factorial times k factorial, and I didn't touch that part. And also, I make some calculation here, this one and this one. I mean, the relevant term, if I open this one, the relevant terms will be cancel each other, right? So at this point, I will reach n minus k times n minus k minus 1. So n minus, I can stop at n minus k factorial, and these two guys will cancel out each other. And I will end up with n factorial, n times n minus 1, n minus 1 times n minus 2, until n minus k plus 1 divided by k factorial. And also I can replace this thing. So this part can be written as lambda to k divided by n to k. And I can get that n to k here and k factorial to here. And then I will not touch this thing. So also, the limit of the product and the product of the limits will be same. That's why I can rewrite this part as the limit of n divided by n, n minus divided by n, n minus 2 divided by n, until the n minus k plus 1 divided by n. Okay, also this will be the limit of lambda to k divided by k factorial, and this is the I didn't touch that one, that part, but just I wrote them separately. So that's mean the limit of 1 minus lambda divided by n to n times limit of 1 minus lambda divided by n to minus k. So this from here and this from here, okay? So this multiplication until this one will be 1, right? Because the limit of n divided by n is 1, limit of n minus 1 divided by n is 1. So all the multiplication of these ones will be 1. Okay, so this part is not based on n, so I can take this one as it is. So which is lambda to k divided by k factorial. Also, this is the definition of the number e, okay, number e, but instead of 1, we have lambda, so I can rewrite this part as e to the lambda, and also e to the lambda, and this part, the limit of 1 minus lambda to n is actually the 1, right? Because this part goes to the 0, and the all calculation, the all limit will be 1. So here I just ended up with a times, sorry, e to the minus lambda times lambda to the k divided by k factorial. Okay, so I have ended up with this one. Okay, now we have defined the probability mass function of the Poisson distribution. But let's check if all possible probabilities, the summation of all possible probabilities is equal to 1. Okay, so this is the PMF of that random variables, and for all each possible values of k, the summation of this term should be equal to 1. So the k will start from 0 to infinity, and the e to the minus lambda times lambda to the k divided by k factorial should be equal to 1. So this is a constant, and it can go outside the summation. And I will end up with e to the minus lambda times summation of the lambda to the k divided by k factorial. And if you remember, this is the Maclaurin expansion of e to the lambda. Okay. If you don't remember this part, please check your the previous lectures, the calculus lectures. Okay. So, and this term will be e to the minus lambda times e to the lambda. That will be equal to 1. Okay, so again, there are some graphs with different parameters, and remember that the Poisson distribution has only one parameter, which is lambda. Okay, so for lambda value is 0.1, I have some graph, and for lambda 2, I have another graph, and for lambda 5, I have another graph. So please check that graphs and see how the lambda values can change the shape of those graphs. Okay, so let's calculate the expected value of Poisson distribution, which is, remember that the expected value of x is simply the x times summation of x times PMF of x. Okay, so this is the x actually here. So that's mean the values that random variables can take, and this is the corresponding PMF, the PMF of Poisson distribution. So the first thing, we can change the index, because the very first value of index is 0. So if I put 0 here, 0 times something will be 0, so that I can omit that one. And let's start from 1. And this will be k times e to the minus lambda times lambda to the k divided by k factorial. Okay. So let's take one of the lambdas outside the summation and change this part as e to the minus lambda divided by lambda to the k minus 1 divided by k minus 1 factorial. So did you notice that this part this part is very similar to this one, right? This one. Instead of k, we just put the k minus, right? So in other words, instead of k minus 1, instead of k minus 1, we can say that j is equal to k minus 1, and we can write j instead of k minus 1. So, and this will be the lambda times summation of e to the minus lambda times lambda to the j divided by j factorial. And if you remember that, that part is the expansion of the e to the lambda, the Maclaurin expansion of e to the lambda. So that's why if I write here e to the lambda, these two guys will cancel each other, and I will end up with lambda. Okay, the expected value of Poisson distribution is lambda, and that makes sense because remember that on average we have lambda customer on average. So the expected value is actually the average value of that distribution. So getting lambda makes sense. Okay, let's calculate the second moment, which is the expected value of x squared, and that will be the summation of k squared. Instead of k, we will just put k squared, and the same thing, the PMF. And again, take one of the lambdas outside of summation, and that will be k times e to the minus lambda times lambda to the k minus 1 divided by k minus 1 factorial. Okay. Now, let's rewrite this part, this k, as this one as k minus 1 plus 1. Okay. In that case, I can write all these things as the summation of k minus 1, this one, times this guy, plus summation of 1 times this guy. Okay, so here actually what I did is something like that. Let's say summation of a plus 1 times a is equal to summation of ai times summation of ba. Okay, so actually I did the same thing here because it will help me to make the calculation simple, such that this one, this guy, what? This is, we have already calculated here, right? Where was it? Okay, here. The summation of all possible values will be equal to 1, right? So here, instead of k, use k minus 1, because in this part, the k is starting from 1, but here, the k will start from 0. So I can simply say that this is similar to that one, and I can say this is equal to 1. And now let's look at this part, which is actually the expected value of x, right? Look, that one. What is this? This is actually this one, right? So let me clear this part, which is, we prove that this is equal to lambda, right? So instead, the k start from 0. So instead of using k, we can use k minus 1, and k can start from 1. So same thing, right? Same thing. So k start from 1, and instead of k, we will use just k minus 1. So we have already calculated this part, which will be equal to lambda. And this part will be lambda times lambda plus 1. And the expected value of x squared will be lambda squared plus lambda. So the variance can be calculated easily because I have already calculated this two term. That will be lambda square plus lambda minus lambda square, and I will end it up with lambda. So the variance of the variance of the Poisson distribution is lambda, and also the expected value of the Poisson distribution is lambda. So, okay, let's look at some example. Suppose that the number of typographical errors on a single page of this book has a Poisson distribution with parameter lambda is equal to 1. So calculate the probability that there is at least one error on this page. So in here, this random variables, it is said to us, explicitly said to us that random variable has the Poisson distribution. But if not, you can think that's the Poisson distribution still, because uh, the basic, the logic behind the Poisson distribution as follows. Mean you have many trials, okay, many trials, and getting the success, the probability of success is very small. So in this example, for example, a single page, let's say, can be divided into many tiny parts, right? And in that small parts, we will look for a mistake, and the probability of that mistake will be really small. So how we can calculate that kind of probability? What was the question? The question is calculate the probability that there is at least one error, at least one error on this page. So what I am looking for, the probability of X will be greater than or equal to 1, right? So it can be 1, 2, 3, so infinite. Instead of thinking like that, we can say which will be equal to 1 minus P, X will be less than 1. The probability of X will be less than 1. So this is also equal to the probability of X will be equal to 0, right? And what was the PMF of the Poisson distribution? Let's this one, right? This one. Let's write there, which is e to the minus lambda times, let me write again, lambda k divided by k factorial, right? So what was the value of k here, which is 1, right? And I know lambda is 1. It will be e to the minus 1 times lambda, which is 1 divided by 0 factorial. This will be 1, and I will end it up with e to the minus 1. So what was my calculation? 1 minus probability of x is equal to 0, and this is e to the minus 1, and I will end it up with approximately 0.633. Okay, this is the probability of at least one error on that page. Let's look at another example. If the number of accidents occurring on a highway each day is a Poisson random variable with parameter lambda is equal to 3, what is the probability that no accident occurs today? So again, that's the Poisson distribution, because on that highway, there are a lot of cars. Each can be thought as a tiny parts, and the probability of getting an accident is really, really small. So if that is the case, I can say that that's the Poisson distribution. Okay, so the probability no accident occur. So I'm looking, x is equal to 0, right? What is the probability that no accident occur? So again, I can simply calculate the product of x is equal to 0. Let's remember the PMF of that, e to the minus lambda times lambda to the k divided by k factorial. The k is 0, so this part will be 1, and this part will be e to the minus 3, and it will be approximately 0.05. So let's look at another example. Consider an experiment that consists of counting the number of alpha particles given off in a 1-second interval by 1 gram of radioactive material. If we know from the past experience that on the average 3.2 such alpha particles are given off, what is the good approximation to the probability that no more than 2 alpha particles will appear? In this example, we are not explicitly say that random variable has a Poisson distribution, but we can think that because imagine that 1 gram of radioactive materials can consist of the million, maybe trillions of particles, right? And only a very tiny part of or a very tiny fraction of them are the alpha particles. So choosing an alpha particle, the probability of choosing an alpha particle is like really small. So that's why we can say that that is the Poisson distribution. So so what is a good approximation to the probability that no more than 2 alpha particles will appear? So that means the x will be 0, can be 0, x can be 1, and x can be 2, right? That is all possible values asked to us, right? That values will be our interest. So it is simply the probability of x will be less than or equal to 2, and that can be 0, 1, and 2. And simply, if you put that values into the PMF, you will get that values. To remember the PMF, e to the minus lambda times lambda to the k divided by k factorial. For example, for the first one, the 0, these guys will be 1, and I will end up with e to the minus 3.2, which is given to us. And the second value is 1. That will be e to the minus 3.2 times 3.21, 3.2 to the 1, and the 1 factorial, that will be 3.2 times e to the minus 3.2. And same thing for this one. In this case, it will be 2, and that will be e to the minus 3.2 times 3.2 to the 2 to the 2, and divided by 2 factorial, and it will give us approximately 0.382. Okay, so this is how we can calculate the probability of random variables that has a Poisson distribution.